What about temperature effects? We know that equilibria are temperature dependent because Kf for kinetics, right? The higher the T, the more we get over the activation barrier. Right? There's our activation barrier. The higher the temperature, the more we get over there because of our Boltzmann distribution of molecules, right? So something cold versus something hot, more of those hot ones are able to get energy over that threshold. We saw a connection between delta G and H and T and S, our standard thermos. So delta H is obviously tied to heat and temperature, but we saw so was entropy. We saw that entropy had a temperature dependence. And we saw a connection between G and equilibria. So now we can link those guys. We can link through delta G. I forget the Triforce. He's got the G-force. We can take our traditional thermodynamic variables, enthalpy, temperature, entropy, and connect them to equilibria. So our quantitative dependence on the equilibrium constant and the temperature can be specified from the following relationship. If delta G is equal to minus RT ln K, and delta G is equal to delta G is equal to delta H minus T delta S, we can just kind of say, well, hey, minus RT ln K is equal to delta H minus T delta S. And we can take that equation and rearrange it for this guy so that we get the natural log of K is minus delta H naught over RT plus S delta S over R, right, because the temperature over temperature would have canceled out. So we have this equation that's set up to say the natural log of K is equal to minus delta H over R times 1 over T plus delta S over R. Now, if you're looking at this and you're thinking, wait a minute, this looks familiar. Have you seen other equations that are like natural log of A is equal to minus delta H naught, or natural log of pressure is delta H over R and 1 over T plus some sort of constant over here? Yeah, you have, right? It's very, very similar mathematically to what we have done with Clausius-Clapeyron, to what we've done with the Arrhenius equation. So it's another, or what we've done to first order kinetics. Right, so we've got this very similar looking equation where now we've got this sucker linearized. We've got this natural log of K related to delta H over R, right? So our slope is going to be delta H over R, and our x-axis could be 1 over T. And then we've got some constant. All right, so we can tie all these things together.